In this video, we're going to take a familiar idea, which is the idea of congruence mod n, and we're going to extend it. We're going to extend it to the setting of an ideal of a ring. So we're going to talk about what it means to be congruent modulo an ideal. So here's a definition. So let R be a commutative ring with unity. And pretty much for most of what we do from now on, we're going to assume commutative ring with unity. Not that other rings aren't important, just because these are the ones I enjoy talking about the most. So R is a commutative ring with unity, and let I be an ideal of R. And just as a reminder, we usually write this as I left triangle R. Sort of like we did with normal subgroups, that left triangle. There we go. Sorry, this is what I was going for. There we are. Okay, so let I be an ideal of R. Then, if x and y both belong to R, we say x is congruent to y mod I. Okay, so not mod an integer, but mod I, an ideal, if and only if there exists some, and let's call it A, some A belonging to I, such that x plus A equals y. Okay, so that's what it means to be congruent mod an ideal, is that I can take some element of the ideal, add it to x, and get y. And because I is closed under taking additive inverses, that also means I could take some element of I and add it to y to get x. Okay, that's another thing that would be true if x is congruent to y mod I. Now at this point, I'd be remiss if I didn't mention what this has to do with the idea of congruence that we're used to. So what this has to do mod n, with congruence mod n. Okay, well, if x and y are integers such that x is congruent to y mod n, well, then that means there exists some k, an integer, such that x plus nk is equal to y. I don't know whether we said x plus nk or x plus k, and I guess it doesn't matter all that much. I'm a style freak when it comes to this stuff. Okay, but look at this. This nk here, this belongs to the ideal generated by n, which is the same as saying the set of all multiples of n in the integers. Okay, so in other words, I can think, well, congruence mod n is equivalent to congruence mod the ideal generated by n, or the principal ideal generated by n. Okay, so if I want to put the idea of congruence mod n for integers in terms of this ideal congruence way of thinking, I would just take the ideal generated by n, and then I'd say what it means to be congruent mod that ideal. Okay, so anyway, that's just to point out that congruence mod n, which we've dealt with for a while now, is actually just a special case of the idea of congruence modulo an ideal. All right, so now let's prove a couple little facts about congruence mod an ideal. Okay, so first of all, suppose x1, x2, y1, and y2 all are elements of R such that x1 is congruent to x2 mod I, and y1 is congruent to y2 mod I. I'm going to claim two things here. First is that then under this assumption, x1 plus y1 is congruent to x2 plus y2 mod I, and also x1 times y1 is congruent to x2 y2 mod I. The upshot of this theorem here that we're about to prove, we're going to prove this in this video, and this, by the way, is a good case of you might want to stop the video and see if you can prove these on your own, because you have the definition right up here. It's just right here. You could use this definition to prove this fact. But once we have proven this fact, what that'll mean is that if we're only interested in congruence classes mod I, then we can take any representative of a congruence class, whether x1 or x2, and we can add it to any representative of this other congruence class, y1 or y2. And no matter what we do, the result of the addition will be the same modulo the ideal, and same for multiplication. So in other words, this is another way of showing addition and multiplication are well-defined modulo I. So here's the proof. All right, we've already supposed that x1 and x2 are congruent. We've already supposed y1 and y2 are congruent, so let's just get to work. Since x1 is congruent to x2, and I'm going to leave off the mod I for now because the only congruence we're talking about is mod I, and y1 is congruent to y2, there exist, let's call them A and B in the ideal, such that x1 plus A is equal to x2, and y1 plus b is equal to y2. Great. So then, well, what does that mean about x2 plus y2? Because I've got these nice little elegant expressions for x2 and y2 here. So I'm thinking if I substitute these in, something good is bound to happen. Let's find out. So I get x1 plus a here for x2, and then y2 is equivalent to y1 plus b. So I can make those substitutions. And then if I just reassociate and commute, because with addition I can do both of those things, I get x1 plus y1 plus a plus b. And we know, since I is an ideal, hence closed under multiplication, or sorry, closed under addition is what I mean, a plus b also belongs to I, because a and b both belong to I. All right, so I know that this is x1 plus y1 plus an element of I. Great. So this means x1 plus y1 is congruent to x2 plus y2 mod I. Awesome. What about multiplication? So for multiplication, I'm going to start out the same way. I'm going to try calculating x2 times y2. I'm assuming that these substitutions for x2 and y2, or these equalities, are still in play, because those were just true based on the fact that x1 and x2 were congruent and y1 and y2 were congruent. It wasn't specific to addition or multiplication. All right, x2, y2 is going to equal x1 plus a, y1 plus b. Okay, and let's go through and carefully use the distributive property. This is going to be x1 times y1 plus b, there we go, plus a times y1 plus b. And I'm going to do something kind of cute here. Rather than distribute the whole thing out, like I'm foiling it, I'm just going to distribute the first thing out. I'm going to get x1, y1 plus x1b. And I'm going to leave this alone. Okay, why would I do that? Okay, well, a and b are both members of the ideal, and the ideal absorbs all multiplication. So since a belongs to I know that this multiple of a, y1 plus b, also has to belong to I. And I also know that b belongs to I, so x1b must belong to I. So that's great. So x1b plus a, y1 plus b also has to belong to I, because I is closed under addition. So what I have here is x1, y1 plus an element of I, which means x1, y1 is congruent to x2, y2 mod I. Super. All right, so that proves that addition and multiplication are both well-defined mod I. In other words, I can switch out representatives of the same congruence class, and the result of the operation will be the same modulo I. Now here's another thing, and this to me is really what gives this congruence way of thinking about ideals its power. This is what really is the major convenience of this way of thinking, because actually a lot of textbooks don't introduce the idea of congruent modulo and ideal. That's kind of my thing, and I didn't invent it. I'm not the only one to have done this, but I find that actually this is a nice convenient way of talking about ideals, and especially quotient rings and cosets of ideals. Okay, so here's a theorem, and this is important. If I is an ideal of R, and again we're going to assume, not because we necessarily need to, but because it's convenient, R is commutative with unity. Okay, so if I is an ideal of R, and X and Y both belong to R, then X is congruent to Y mod I, if and only if x plus I equals y plus I. So remember that when we talk about a quotient ring, we're talking about the set of all left cosets of I under addition. All right, so what this says is that we can talk about two cosets being exactly the same as long as we know that the representatives are congruent mod I. So that means that we can do a lot of operations within the quotient ring R mod I using this congruence idea rather than having to write cosets all of the time, which is kind of nice. Okay, so let's prove this theorem. Okay, so first let's suppose x is congruent to y mod I. I think I actually picked the more intricate and harder one to do first, so that'll be kind of nice. It'll be nice later, not so nice right now. Okay, so then there is some a in I such that x plus a equals y. Okay, great. But now we have to show that x plus I equals y plus I, and that's a set equality proof. So to do that, we're going to first show that x plus I is a subset of y plus I. So let's assume that we have some element of x plus I, and I'm running out of letters. Let's just call it r. Let's assume that r belongs to x plus I. Okay, so then r is equal to, and I want to say x plus a, but a is already defined, and we need to leave that put. So let's say r is equal to x plus b for some b and I. Okay, so now let's just think about this. We want to show that r belongs to y plus I. So how are we going to make that happen? Well, we need to use the relationship between x and y, I think. So we know that x plus a is equal to y. So we can also say that x is equal to y plus negative a. And we know negative a also belongs to the ideal. So that's good to know. All right, so r is also equal to, and I'm going to substitute for x this thing y plus negative a. Y plus negative a plus b. Okay, but look, negative a and b both belong to I, so I believe that means this belongs to I, and so r belongs to y plus I, because there we have r expressed as y plus an element of the ideal. Okay, so that means x plus I is a subset of y plus I. Now let's go the other way. I think the other way is a little bit more straightforward. We don't need to use the opposite for this. All right, so to show y plus I is a subset of x plus I, let's assume that r belongs to y plus I. And I'm just going to recycle the symbol r. Okay, so then r is equal to y plus, let's call this something different. I don't know why I feel compelled to use a different symbol here, but let's say c for some c belonging to I. Okay, great. Well, we know that y is equal to x plus a. That's this equality up here. Okay, this is looking very, very festive with the green and the red. So r is equal to, and then y was x plus a, so x plus a plus c, and that's, I'm just going to reassociate that so the main point is more visible here. X plus a plus c, and since a plus c belongs to I, because a does and c does, this means r is an element of x plus I. Okay, so y plus I is also a subset of x plus I. Thus, I think we've shown that these two cosets are equal. X plus I is equal to y plus I. Now I'm just going to mention there's a huge shortcut I could have taken, and maybe I should have taken it because I should probably be modeling how to do these things more efficiently. But here's a much easier way. I'm just going to switch colors here. There we go. Okay, so here's a much easier way. Okay, these are cosets. I mean, they're cosets in the group theoretic sense. They're cosets of an additive subgroup I. And one thing we know about cosets is they're either disjoint or they're exactly the same. So if I'm trying to prove that x plus I and y plus I are exactly the same coset, I just need to show they have something in common. So show that x plus I and y plus I have a common element. Once you've done that, that means that they are exactly the same coset. And what element do they have in common? Well, certainly y belongs to y plus I, because it's y plus 0, and 0 belongs to I. And I think that we're assuming that y is equal to x plus a, where a is an element of the ideal, so that means y also belongs to x plus I. And there you have it, there's an intersection, so they're exactly the same. You don't have to do this whole element chasing proof. I just feel like it's good therapy to do it sometimes. Okay, so that's one half of the proof. Now we got to do the other half. Okay, let's remind ourselves what we were proving here. Okay, so x is congruent to y if and only if x plus y equals y plus I. I think the other half is going to be a little bit more accommodating for us. Okay, so let's assume x plus I equals y plus I. Okay, so then that means they're exactly the same set. So since y belongs to y plus I, because it's y plus 0, I'm kind of using some of the same reasoning we just did. And y plus I is the same as x plus I. That means y also has to belong to x plus I, because they're exactly the same set. If y belongs to one, it belongs to the other one. But because y belongs to x plus I, we have y equals x plus a for some a in the ideal. And look at there. That's exactly what it means to say that x and y are congruent. So x and y are congruent mod I, and I think we're done. All right, so just one more little thing. I know that this video is already running a bit long, but what all this means is that I can actually use a more convenient way of talking about elements of R mod I. So here's a little bit about how we talk about R mod I. So normally we talk about elements like a plus I or x plus I. Every element of R mod I is a coset of I. Okay, but now there's a couple of things that we can do. First of all, let's just suppose that in some specific situation, I'm not going to say what situation right now, but suppose we're given that x plus I times y plus I is 0 plus I. Okay, suppose that's something we know, we want to prove something about that. Well, in the past, we would have had to say, well, the definition says that is xy plus I equals 0 plus I, and then we'd have to work on interpreting that. We'd have to say, oh, what does it mean for x plus y to be the same as the ideal I? Oh, my goodness. But now, this theorem gives us a way to interpret that. We know that xy plus I is the same as 0 plus I if and only if xy is congruent to 0 mod I. And to be 0 mod I means that xy plus some element of the ideal is equal to 0. So in other words, xy is equal to negative a, which negative a is also an element of the ideal. So really all this is saying that xy belongs to the ideal. Okay. And another thing about this is, eventually we sort of grow out of having to constantly talk about the cosets, like having to refer to everything as a coset. The way that we avoid that is, so I'm going to say in the future, and by future I mean starting now, we can write x plus I as, and I think you're going to find this notation to be somewhat familiar, as brackets x. Okay, where have we used brackets x before? We used brackets x to refer to the congruence class of x. Congruence class of x mod I. Okay, so again, we're borrowing ideas from the idea of congruence modulo n, which we use for the integers. So in the future, instead of having to write x plus I this, y plus I that, we can just write brackets x, brackets y, and that's a little bit more convenient notationally, just not as clumsy looking at times. All right, so anyway, that's everything about congruence modulo n ideal. We'll use that language from now on to talk about some theorems about factor rings. Wow, that was quite the expansive video. Okay, thanks for your patience.